I wanted to take some time to talk about Rust's role in sustainability and global warming and all that stuff. You might have seen this paper floating around the internet, this chart, which was in the paper and was mentioned in a AWS uh, speech at reInvent, and was also in a corresponding blog article, and sort of blew up on Twitter where people were complaining about it and that sort of thing. People complain about things on Twitter all the time. I figured this is just more people complaining about stuff on Twitter. But they actually had some good points. What the paper was trying to do was answer four different questions. Can we compare the energy efficiency of software languages? So, can we compare these things? Two, is the faster language always the most energy efficient? Three, how does memory usage relate to energy consumption? I'm going to sort of ignore the fourth question because just personally, I think trying to automate the decision of what language you should use is sort of a silly question. There's so many other things that are involved. And that was a common complaint on Twitter, which is that just looking at the languages is such a simplification of the problem, which is true. And they actually admit that in the paper. So I would not worry too much about that. But the benchmark was based on an online competition called the Computer Language Benchmark Game. I have the link to that in the description. But they were basically saying that this is not a good way to do it. So the entire paper is invalidated, which is fine. But if we're going to talk about it, we sort of, you either decide that the whole thing is useless and you can't get anything out of it, or you work under the assumption that the benchmarks are okay enough and broad strokes, we can talk about it. We're just going to assume that we can talk about it, which might not actually be true. So we're just going to use the general ideas. So one of the first things we have to understand is how energy actually works. So the equation for energy is energy in joules is equal to the power in watts times the time in seconds, right? So it's just the amount of power, which is just the electricity here, over time, and that's energy. So, which makes sense, right? If we think about writing a program and the program runs, the amount of time that the program took is directly proportional to the amount of energy that it used, but it is with respect to the amount of power that that program was drawing while it was running. There is a general feeling of just like having our fingers crossed to hope that the increases in performance speed will directly affect the increases in energy efficiencies. And while that's not necessarily true, we would like it to be, because what we really want is speed. We're just sort of hoping that this new goal is measured by the same metrics that we were already targeting. I tend to agree with Peter DeSantis from AWS when he says the greenest energy is the energy we don't use. So in order to read this, you can see under energy, time, and memory, it all starts at 1.0, because what they did is they took the best performing language and they set that as the baseline. So you can see we have this awkward jump from C to C to Pascal. What is helpful to know is the baseline number. So the baseline number here used for C was 57.86 joules. And what you do is you just take whatever number is in that column, multiply it by 57.86 joules, and that's the number of joules you had for that language according to this paper. And as you can see, Rust is at 1.03. Python is near the bottom at 75.88. Another one of the broad strokes takeaways is that there's a big difference between compiled languages and not compiled languages, which is one of the main reasons why comparing Python to Rust is like a strange thing to do anyway. I don't know a lot about C or TypeScript or JavaScript or C++, but apparently C programs are valid C++, and it's weird that C++ would do so much worse than C, which sort of makes sense. And TypeScript and JavaScript are in a similar situation. I don't know enough about C to hate it. I just know that I used it in my undergrad class, and I hated it. The complaint that they admit in the paper is that software changes. Open source software is inherently a work in progress. That's what it is. That's why we love it. And hardware, Moore's law, it changes all the time, right? So that happens. Things can pass each other in the ranking. That happens. But you know how hard it is to do science if you can't take a problem and break it down into smaller parts? It's like you have to hold certain things still. You just have to. Another cool thing, though, is that Elon Musk tweeted about Rust in response to somebody and saying that he likes Rust. But that for his purposes at Tesla, it doesn't make sense to use Rust because you need to be so optimized that you have your own tightly wound C plus a optimized C compiler is always going to be better, which is probably true. And I mean, if you can afford to hire like a bunch of expert C programmers and then write your own customized compiler, then more power to you, you know? He also said that if you do not need those super optimizations, you should never use C, which is probably right because there's just so many ways to hurt yourself. One of the main questions here is, can Ferris save the planet? And the answer is probably not. We need to look at the scope, right? So like what is the target area that we can actually affect with Rust? It was estimated, I think, a couple years ago that data centers themselves consume about 1% of energy worldwide. And an important thing to note about this is that we've been using more and more data centers, and the demand for that is really increasing. But one of the problems is that so far, the innovations in efficiencies have been able to keep up with that demand. If that were to stop and the demand were to increase, then the 1% number would go up. And I would guess that it would go up pretty quickly. So the cool part with that is that a very small percentage of the world's population actually has even access to be able to program. So even if you're like me and terrible at Rust, you have a opportunity to have a large impact on that 1% of the energy used in the world, which is really cool. But with that being said, you know, everything I do is just like on my computer, which is not, it's basically nothing. But if you look at these data centers and these clouds, like if you write one piece of software and it runs, thousands of times a day, every day, forever, like that's a lot. That could be a lot. You could have a big impact by just making that better. That's not even to mention like things that are for energy purposes basically the same as data centers, like phones are basically the same thing. They're just instead of being in a warehouse, they're sort of spread out into a bunch of little pieces and in our pockets. Let's see what else. Once government regulation started taking effect, that's when we started to see all of these initiatives start to pop up. One of the things that happens is that just like businesses have accounting standards for the money that goes in and out and is used in the business, they're trying to also have emissions accounting, basically. So everything is tracked as to what you use and what you contribute to the world's carbon footprint. What's important about this is that the way that the energy accounting works is that anything that happens on the cloud infrastructure, that is the responsibility of the cloud provider. Anything that you as a customer run, all your workloads that you run on the cloud, those are your responsibility. So it sort of separates the the uh, the development of the workload from the development of the physical location. Data centers have a incredible amount of economies of scale. It's like not just anyone can build a data center, like a lot of things that you would just not be able to really do on-prem, right? Like you're not going to build a wind farm or a solar farm or something like that. The accounting doesn't just extend to the electricity that you use. It also extends to like if everything goes down, you have to use a backup generator. It counts that. If you have to build that solar farm, it counts what it takes to build it, right? The gasoline and everything. And it's much easier once that is already built for you to just use it. And one of the interesting things is that if you, right, or if I run a company that is almost entirely software, and I now have to meet these environmental emission standards, then I can just offload all of my work to the AWS cloud and sort of make up the difference, right? Because if the cloud that I'm using is 100% renewable energy, then I now have a large portion of my business that is meeting the standard. And all I have to do is make up the difference for the things that are not there, which is a big competitive advantage because if I have to meet that regulation, I might choose your cloud service over someone else's. Part of cloud providers' service level agreements are that they have to have a certain level of redundancy, right? You have this marching of nines, like are we 99.99% uptime? Are we 99.999% uptime? Right? How many nines do you have? And one thing that can happen is that you can start to take some more of the non-vital services and relax those service level agreements so that they have things like less redundancies, which inherently saves power. Right? That can really dig into your competitive advantage as a business as far as like affecting what you give to the customer and how pleased they are with your product. I would not expect people to sacrifice from that area so much. That's my other question is like, does this only matter at scale? I would love to know, like, does that bother you? Does the fact that Rust is energy efficient even matter to you? Right? I like that it's more efficient, but Rust is fun for reasons that have nothing to do with energy efficiency. Another interesting thing is how shareability affects these things. All of these cloud providers, right? That's one of the economies of scales you have is that if one part of the company figures out how to write code in such a way that it draws less power and provides the same output with the same inputs, then they can share that same method with another part of the company, right? And this is true for all cloud providers. So there's a lot of things that aren't measured and might not be measurable, like how how shareable are improvements in one language versus another. I like Rust. From what I've seen, Rust has been pretty shareable. You know, the documentation is great. It's readable. I understand it, so it's got to be good. Obviously a big fan of Rust, but there does seem to be a lot of cherry picking going on when it comes to examples like, oh, this runs faster and with less memory to boot, and it's easy to write, and there's no foot guns and all that stuff, which is sort of unfortunate because I don't think Rust needs to cherry pick. I don't think it needs that. It's sort of great. You can just give real examples. Sometimes your use case is going to be worse than something else. That's okay. So far, it seems like Rust is really well suited for running in these cloud environments. And is it a coincidence that AWS, Google, and Microsoft were all founding members of the Rust Foundation? I have to believe that the performance that people are seeing in the energy efficiencies of Rust led in some part to these big three cloud providers becoming the founding members of the Rust Foundation. It's like a whole world of things that are being worked on that just sort of go unnoticed unless you're directly looking at them, which is cool. You know, we weren't working on this stuff before, and it's good that it's happening. It might be too late. I hope not, but we got to start somewhere. I'm not an authority. I don't work for a cloud provider. I'm not even good at Rust. So if I got something wrong, if you disagree, please let me know.